Alright, so I wanted to make a short video about the careful definition of a limit. In particular, I'm looking at the two-sided limit of some function, and we're looking at a point which is, well, it doesn't have to be in the domain of the function, alright? Like the middle graph here, x equals to a is not in the domain of f. See that circle in the graph there? Right, but for the left and the right graphs, a is in the domain of the function. But the limit here exists for two of these, but not this one. The idea of a limit existing, what it's trying to capture is that if you zoom in on the point, the limit point A, right, then if the limit is L, which I'll graph here with a blue horizontal line. Alright, if the limit is L, and so here, L, right, then what that means is if you pick some band of values about L, say plus or minus epsilon, alright, so that would be something like plus epsilon, minus epsilon, alright. Alright, here, I'll draw it here. So, but here's the deal. For any band you pick, I'm just drawing kind of big ones, but the idea is you can make epsilon as, that's supposed to be minus, you can make this epsilon as small as you like, right? Well then, what you can do is you can consider points, and I'm excluding the limit point. The way the limit works is it doesn't care about what happens at A itself, but just what happens near A. The point is you can choose, say, a delta, so that if you go to A plus delta, A minus delta not included, alright? And you track back from there, alright? Where the image of the function goes. So I'll draw the image, try to illustrate the image of the function in, let's say, green. I haven't used green yet, right? So here, this graph is like here to here, right? And if you pick any point, in there, it's within this epsilon band, right? In other words, for each epsilon greater than 0, I can choose some delta, all right, which is small enough so that the graph of the function fits inside the box there, which I'll shade. So in some sense, it's saying you can zoom in on the graph, and it's going to fit in the little zoom box, but you don't have to care. There's one caveat. You don't have to care about the limit point itself. In this case, the limit point is A, okay? Limit point. And again, the limit point A doesn't even have to be in the domain of the function, and the limit's still defined. So like over here, lots of different deltas will do. Pretty much I can choose anything all the way out to like here for delta. I'll make it like this. Here's A plus delta. Here's A minus delta, right? So A is not included, so it's kind of like a little TIE fighter, right? And so you go back up here, okay? Where's the function? Where's the function go to? Well, the function goes from here, right? We don't care about A itself, there's a hole in the values over to here, right? And you can see that the function is inside the epsilon band for that choice of delta, right? So that's what you need to be able to do that for the limit to exist. So basically for the limit to exist, the function can't do something like this. This over here won't do it. Again, the limit point is A. Limit point of A, limiting the value of the limit, or the limit value, is L, quote unquote. Now here, you probably recall that f is continuous. For f to be continuous, we need f of x to go to f of a, as x goes to a, all right? So f of a here would be that. so if this limit was going to exist, if this function was going to be continuous, all right, for the limiting value L, we're forced to make the limiting value L here if we're looking for continuity, right? So if you look at any epsilon, and I'm just drawing one, right? But it's pretty clear that for any epsilon you pick, right? Well, I mean, you just have to find one epsilon it fails for, right? So for this one, for example, if I look at this epsilon, there is no possible choice of delta, no matter how small I make delta, right? Right? So if I make delta this small, for example, so here's a plus delta, here's a minus delta, right? So basically you're looking for where the graph goes in this window, vertical window, so to speak. And as you can see, it does not stay within the epsilon band. Yeah, the function behaving here to here, right? But down here, oh no. And let me just point out that, I'm going to have to draw a little arrow here. I guess I'll use orange. So if you look at the points right there, the distance, which we could write as the epsilon value of f of x minus L, right? Those are greater than epsilon. They are not, and this is the distance. If we take the epsilon value of the difference between two things, that gives us the distance between those things on the number line, right? And so these points in the graph are further than they're allowed to be for that epsilon. And it doesn't matter how small I make the delta, I can't fix that. There's this jump discontinuity here, and the limit simply will not exist. Now, if you were to define a left limit, right, as x approaches a with a little minus on it, then yeah, that limit would exist. Or if you were allowed right limit, x approaches a from the right, then that limit would exist, but they would also not be equal. All right, but I'm not talking about left and right limits in this little talk. I'm just going to talk about double-sided limits. So I would simply say that here the limit does not exist. So that brings us, I hope that gives you some sense of where I'm coming from when I make the following definition. Here's the definition. If f is a function on R, so that means it's a function to and from the real numbers for which there exists a deleted neighborhood about x equals to a. Let me just put it in parentheses what that means. In other words, the notation I use in my notes I think is this: b delta a sub naught. To be more specific, it's x in the reals such that 0 less than epsilon value of x minus a less than delta. All right. If there exists a delta greater than 0, of course, for which that is a subset of the domain, right? Then that means that a is what's called a limit point. All right. Then a is a limit point of f. All right, in this context, so then given a is a limit point, we say the following. The limit as x goes to a of f of x is equal to L if and only if the following. All right. For each, let me scooch it up a bit here. All right, for each epsilon greater than 0, there exists delta greater than 0, such that 0 less than the epsilon value of x minus a less than delta implies that the absolute value of f of x minus L is less than epsilon. Alright, so that's what we need to be able to do. For each epsilon greater than 0, we need to be able to pick a delta greater than 0, such that whenever x is between, x minus a is between 0 and delta, we have that. Now let me just, that's the definition, let me unpack it geometrically a little bit, alright? So this right here is saying that x is within delta units of x equals to a, right, of a, but we don't consider x equals to a necessarily, right? That's what this 0 less than that. If it was equal to 0, then x would be equal to a, but we don't have to consider that, right? And over here, what this is saying is that the distance from f of x to L is smaller than epsilon units. That's what that says. Alright, so that's the careful definition of a limit. Let me do some simple and some less simple examples using that definition. Alright. So example 1. Example 1. So suppose we want to consider, let me start with something really, really easy. The limit as x goes to, let's say 3 of 2x plus 1. Alright, so you guys know what that should be. That should be 2 times 3, which is 6, plus 1, which should be 7, right? Alright, so let me show you a little bit of scratch work here. This is a claim. Let's prove it using epsilon-delta definition. So what we want, here's our scratch work. Scratch work, this is not the proof, this is just, preparing for the proof. So what we want is the absolute value of 2x plus 1 minus 7. We want to make that less than epsilon, right? That's our goal. And so if you simplify that, that's 2x minus 6, right? Which is 2 times the absolute value of x minus 3. Now, you notice I get control of what? I get control of the absolute value of x minus 3. I get to make that less than delta, right? That's what I get to assume in the implication. So that makes a pretty obvious choice. If I make delta equal to epsilon over 2, certainly if epsilon's positive, then epsilon over 2 is positive, right? Then if I do that, then when I go back up here, that will be less than 2 times epsilon over 2, which will be epsilon, and then we'll be good to go. Okay, so that scratch work is all I need to do in order to be pretty sure that when I do the proof here, it's going to work. So let me show you the proof. Here's the proof. Let epsilon be greater than 0, and choose delta equal to epsilon over 2. Suppose x is a real number with 0 less than absolute value of x minus 3 less than delta. Consider the absolute value of 2x plus 1 minus 7 is equal to the absolute value of 2x minus 6. Right? Which is, and I'll stack it here, that's equal to 2 times the absolute value of x minus 3, right? Which is less than 2 times epsilon over 2. Because my delta is epsilon over 2, right? And so of course that's equal to epsilon, hence 0 less than absolute value of x minus 3 less than delta implies that the absolute value of f of x minus L is less than epsilon, where f of x in this case is 2x plus 1, and my limiting value L is of course 7. So therefore, by definition of limit, and I think, I don't know, this, and by the definition of limit, I think that's something that mostly Calculus 1 students write when they're in suitably formal Calculus 1 courses. I think people who are actually analysts kind of dispense with this sort of thing. I don't know. This is, well, whatever. Anyway, therefore, by the definition of the limit, we conclude the limit as x goes to 3 of 2x plus 1 is equal to 7. And there you go. That's the end of the proof. The fact that I did things over here does not oblige me to not do them over here, okay? The proof must be self-contained. This is just preparing. Now, another example I can give here. My next example will be considerably easier. So here, example 2, but perhaps disconcerting. My claim is that the limit as x approaches, let's say x naught, of a constant c is just equal to the constant. Alright, so here, I'm just going to do the proof straight up. So here's the proof. So we let epsilon be greater than 0, and you can choose delta to be whatever you want, but we got to make a choice, so I'll choose delta equal to 1, which is of course greater than 0, right? Let x be a real number, and 0 less than absolute value of x minus x naught less than delta. Observe that the absolute value of c minus c is equal to 0, which is less than epsilon. As you can see, it had nothing to do with delta whatsoever, right? Hence, the limit as x goes to x naught of c is equal to c. Okay, so there's a stupid proof. All right. Let me show you another. I guess it's not stupid, but it's not hard either. Example 3. Suppose we want to show that the limit as x goes to a of mx plus b. My goodness, what was that? Oh, crafts. Mx plus b is equal to, of course, you know what it is. It's ma plus b. Alright, here I'm assuming, of course, that m, b, and a are given real numbers. Not necessarily positive, but real numbers, alright? So, if you think about this geometrically for a bit, I guess I'll do some scratch work, basically, just to not make it too mysterious. So scratch work for this one. Basically, we want mx plus b minus ma minus b, so the b's cancel, right? And you get m times x minus a, right? Which is the absolute value of m times the absolute value of x minus a. You want this to work out to be less than epsilon, right? And remember what we get? We get to have that 0 is less than absolute value of x minus a is less than delta. So given the fact that we control the horizontal, right? We can control the vertical by just linking them. Basically, I'm just going to make delta equal to epsilon over the absolute value of m, and that'll do it. I am assuming that m is not equal to 0, right? If m is equal to 0, that takes us back to example 2 anyway. We already covered that. All right, so let me do the proof carefully. Proof. All right, so I know these are English professors would be horrified. The lack of style here. Let epsilon be greater. It's always the same starting point. It's like, imagine you wrote a fairy tale and you began with, long time ago in a land far, far away or whatever it is. I think Star Wars has corrupted my thinking. How's it go? There's, you know, the typical starting. It's like, oh, it's so cliched, you're not very creative. Well, we like this kind of cliche in math because it helps us to know that the student's actually paying attention. And I guess it's a happy place of a good analyst or something. Let epsilon be greater than 0. And choose delta equal to epsilon over the absolute value of m. Now that clearly epsilon over the absolute value of m is positive, right? If you choose a delta which is negative, well, that's a pretty clear giveaway. You don't know what you're doing. Hi, Mr. Ant. Haven't seen you in a while. Welcome back. I don't really mean that, though. I am going to kill you. It's only a matter of time. Star Wars style. Okay, I'll let him live. I'll let him live. I'm trying to give you a reprieve. Get out of here. Shoot, shoot. Shoot. I can't kill you in front of the vegan audience. Come on. Shoot, shoot. I'm sorry, who am I talking to? Anyway, oh, yes, alright. So then, suppose x is a real number and 0 is less than the absolute value of x minus a is less than delta, which, by the way, again, is equal to epsilon over the absolute value of m. Consider. So the way math proof works, right, is if I write this up here, then it's read top down. I don't read it bottom up. That would be confusing. So here we go. Absolute value of mx plus b minus ma minus b. You're like, that's so old, you already did that. I know, but we have to do it again. So this is the absolute value of m times x minus a by algebra, which is equal to the absolute value of m times the absolute value of x minus a, right, which is less than the absolute value of m times epsilon over the absolute value of m, which is equal to epsilon. Consequently, right, we have now shown that 0 less than delta implies f of x minus L is less than epsilon, so hence the limit as x goes to a of mx plus b is equal to ma plus b by definition of limit, right? As you may have noticed, I'm getting tired of writing by definition of limit. So, all right, so there's a proof that linear limits exist and they go to what you think. All right. All right. Well, let me do one that's a little bit more kind of out there. So here's a sort of a theorem. If the limit as x goes to a of f of x is equal to L sub f, and the limit as x goes to a, look, his friend came, of x goes to a of g of x. It's not food, dude. Why am I doing parentheses? Oh, fine, I'll give you some too. I'd be jealous. Limit as x goes to a of g of x is equal to L sub g, right? Where L, you know, fine, let me write something stupid, but some people feel the need. L are real numbers, and what else they would be, but whatever. Then, surprise, surprise, the limit as x goes to a of f of x plus g of x is equal to L sub f plus L sub g. So this is a theorem. Additivity of limits. Ultimately, this leads to the additivity of derivatives and all kinds of other fun things. So let me show you how to prove this. And I'm not going to show you the scratch work because, you know, the proof is more fun to see like this. So here we go, proof. So assume that x equals to a is limit point. I mean, I guess I could assume that by just writing these things, but anyway, limit point of f and g where the limit as x goes to a of f of x is equal to L sub f, and the limit as x goes to a of g of x is equal to L sub g. Let's let epsilon be greater than 0 and choose delta sub f greater than 0 and choose delta sub g. Oh, let me do one thing at a time. Delta sub f greater than 0, sorry, such that whenever we have 0 less than f sub value of x minus a less than delta f, well, that implies that the f sub value of f of x minus L sub f is less than epsilon over 2. Now I can do that because, remember, the limit existing for f means that I can do it for any epsilon, right? So in particular, I can do it for epsilon over 2. This epsilon greater than 0, we're going to come back to before you know it. And choose, well, once we do it for f, you know what we're going to do for g. Delta g greater than 0, such that 0 less than f sub x minus a less than delta g implies that the f sub value of g of x minus L sub g is less than epsilon over 2. Okay, now the I should get rid of the and here and make that a capital C for the English majors out there. There we go, better. Now I can do this because of the data which is given, because the limits exist, right? Now, finally, choose or construct, whatever you want to say. Let's say construct delta equal to the minimum of delta f and delta g. They're two things that are positive, and this, of course, is less than delta sub f, less than or equal to delta of f, and it's less than or equal to delta sub g. So in other words, notice 0 less than f sub value of x minus a less than delta, well, that's less than or equal to delta sub f and delta sub g. So if I assume that x is within delta units of a, it's automatically within delta sub f units and delta sub g units of a, which means I get both of these inequalities for such x, right? Thus, if we look at the absolute value of f of x plus g of x, right, minus parentheses L sub f plus L sub g, I want to show that this quantity is less than epsilon. That's tantamount to showing that, hello again. That's tantamount to showing that being within delta units of limit points implies being epsilon units of the alleged limiting value. So anyway, this is equal to the value of f of x minus L sub f plus g of x minus L sub g, just distributing things and reordering them. But if you look at that, they've got two things, right? There's this, and then we're adding to that. And triangle inequality says that's less than or equal to the absolute value of f of x minus L sub f plus the absolute value of g of x minus L sub g. All right, but I think you know where we're going with this, because we've already chose delta, so that we want to have our cake and eat it too. And so this, of course, is less than epsilon over 2 plus epsilon over 2, also known as epsilon. And consequently, therefore, I'll use the other notation, f of x plus g of x goes to L sub f plus L sub g as x goes to a by the definition of the limit. And there you have it. That's how to prove that limit law using epsilons and deltas. It's really not much harder to prove that you can pull a constant outside of a limit, but I'll leave that to your imagination. Let me do a couple more examples here. Since I have not, it's been on a pretty good run, I haven't seemed to have made a significant mistake yet. In a half hour of talking about this stuff, it's somewhat rare for me, so I'm gonna stop here and start again.